think we can move on with Arsham Ghavasieh. Arsham graduated Addis Bachelor in Physics from Shiraz University in Iran. Then he moved to Italy, I think to Trento University, where he did his master in physics, completing the master in 2016. And now he is doing his PhD, always at Trento University, but I think perhaps at Fondazione Bruno Kressler, primarily. And his interests are, I guess, primarily on real-world networks. And in fact, he will present a talk on diversity of information pathways drives scaling and sparsity in real-world networks. So please, Arsham, the floor is yours.
Hi, thank you for the kind introduction, and thank you also for inviting me. It's a pleasure for me, definitely. I'm trying to share the screen, and I'm also hoping that my internet connection would be strong, because I realized recently that in Padova, the internet connection depends on the weather in some way. So are you seeing my PowerPoints now?
Yes, but it is not full screen at the moment.
Okay, let me just... So yeah, today is rainy, and I hope that the internet connection would be good. So yes, I'm a PhD student of physics in Trento. I work on...
Arsham, what I see at the moment is something that it is cut at some edges. I don't know if this is only for me. But
I don't know, because let me do it again. How about now?
It's the same.
Oh.
So perhaps it is better that you leave
doing it again. So let's see what happens now. So better?
Again the same. Again the same.
Try to share the full screen while sharing.
Okay. So share entire screen.
Yeah, that's what I did before, maybe.
So now probably you are seeing the PowerPoint?
Now it's better. Now it's better.
Okay,
now we see everything. So please
great.
go. Thank you.
So yes, I'm a PhD student at Trento University, working also with FBK, Fondazione Bruno Kessler. I'm working with Manlio De Domenico. He is currently in Padova University, so I'm also in Padova University. I'm going to stay for the last year of my PhD here. And I'm very thrilled to talk about this very recent work of ours that is about the diversity of information pathways in empirical networks. I think this work is targeting one of the fundamental problems in network science today. And that problem is that, networks in real world exhibit some topological properties that are very interesting, like they are at a balance between being connected and disconnected. They are sparsely connected. In other words, they are between segregation and integration. There are some modules shaped inside these networks that are more connected inside than outside, but then the outside connections are not just too few. And these networks are between order and disorder most of the times. It is well established. And this work, we are trying to use a statistical physics of complex networks to provide an answer of why these topological features emerge in real-world networks. So the outline of the talk would be, I start with explaining what is complex information dynamics, which is a key aspect of all these systems, whether they are biological or social or informational. Information dynamics is a key aspect of complex networks. Then I move to network density matrices. I try to introduce them. I try to give you an overview of them, because I'm going to use this framework. This is a very recent framework in network science that is gaining momentum. Maybe you have heard about it before. And then I move to the new work that is about the conflict between response diversity and coordination in real-world networks in complex networks. And then I will show you how we can use this mathematical framework, this density matrix framework, the statistical physics of complex networks framework, to derive some scaling law for networks in real world to explain their sparsity, to somehow explain their modularity and small-worldness, some topological features that they exhibit. And then we will, of course, conclude. So let's focus on complex information dynamics. Regardless of what complex network you are studying, information dynamics is a general term that can explain, that can describe many things in that system. Assume, for example, neurons that are connected in a network by synapses and they exchange electrochemical signals, or people that exchange information in social media, or crowds traveling from place to place in urban areas, or proteins exchanging biochemical signals, and even flights traveling from continent to continent, shaping a global network that connects every place. These are all networks in which something flows that is fundamental for how the network is operating. And information dynamics or information flow is sort of an umbrella term that describes all these physically different phenomena in these networks. It's a sort of general and abstract thinking about all these things. The way information flows in these networks depends on the network, on the shape of the network, on the topology of the network. And when we look at real-world networks, we see that they share many topological features, like a small-worldness. A small-worldness is the feature of complex networks that are more or less like lattices that we deal with in physics, but with some random connections here and there that connect distant nodes together. And this is called a small-worldness, and it changes the flow of information drastically. Also, the complex real-world networks are sparse. They don't have a lot of links, but they are connected in somehow. So the topology is somehow smartly and efficiently connecting the nodes, but it is not overdoing it. And there is mesoscale organization in the topology of complex real-world systems, meaning that groups of nodes shapes communities within which they are more connected than outside. But then they are also connected outside. This is not like there are groups of nodes that are totally separated from the rest of the nodes. And these topological features repeat themselves across systems, from neural systems to biological to social networks to transportation. And this is very interesting. And it is 2 decades of network science dedicated to observing, to describing this phenomenon, and to somehow explaining it. If you want to see the effect of these topological features on the way information travels in these networks, you should couple these structures with dynamical processes, the things that we do a lot. We couple the network with diffusion dynamics, random walk dynamics, synchronization, reaction diffusion, and more recently with highly nonlinear dynamical equations like neural. But the goal of this study is to answer, or to provide an answer of why small-worldness emerges in complex networks, regardless of the domain, regardless of whether it's biological or social, why the networks in real world are sparse, why they show mesoscale organization. And we try to do it using a theoretical framework based on a statistical physics of complex networks that I'm going to give you an overview about. And this is the network density matrices. So to begin with, in physics, we always try to define a state for a system that we are studying, and then from that state, we try to derive different things, and we try to explain different things. For instance, in deterministic simple systems like Newtonian mechanics, we have the position momentum vectors, or in quantum mechanics, we have these wave functions. And these are one-dimensional mathematical objects that characterize the state of the system. And to have quantum system under the deterministic title, I have to emphasize that I'm talking about closed systems, not open systems. But then there can also be a stochasticity. So you are not really sure. There is uncertainty about the state of your system. And then you are dealing with a probability distribution that characterizes the state of your system. And it is way better for complex networks, complex systems that are very hard to directly observe, very hard to measure them part by part, and because they are large, because they are highly interacting. And apart from probability distributions, there is also density matrices in quantum mechanics with some potentials, and I'm getting into that, how they can apply to classical complex systems. So we have classical network information theory. This is an example. This is often based on probability distribution, and this probability distribution is often the distribution of degrees among the nodes. Degree is the number of connections a node has. So the probability of that would be like you observe all the nodes in your network, you draw a distribution for that. It can be Gaussian, it can be Poissonian, and then you have the state of your network. You can calculate its entropy. It means something definitely, and then you can use this distribution to learn about another network that might share some characteristics with this network using the Kullback-Leibler entropy divergence and many other information theoretical tools that you can use to extract knowledge about the network. But this approach, the classical information theory approach, is limited because it highly depends on the local features like the nodes and its connections, and it misses the topological correlations. I give you an example. In some networks, the nodes that have high degrees tend to connect with nodes that also have high degrees. So there is a correlation between high degree nodes. This is something that we call rich globs. When you only look at the degree distribution, you don't see this sort of topological correlation. But of course, this approach is useful. What I'm going to focus on in this talk is density matrix. That is a generalization of the concept of probability distribution. We are all physicists, so you know it very well. But you can define a matrix, and based on that, you can have your entropy and you can have your Kullback-Leibler entropy divergence. And this matrix should satisfy some criteria like being positive, semi-definite, Hermitian, trace one. And the diagonal elements can encode probabilities. But the most important thing for me is the fifth characteristic that I'm writing down. That is the off-diagonal elements of the density matrix encode correlations. So now I'm having a state. If I have a density matrix for a network, I'm having a state that in addition to the properties of the nodes, it is also encoding things, properties about how nodes are correlating together, how nodes are associated with each other. And this is very important for us as network scientists because we always care about how things relate to one another. In 2016, there was Manlio de Domenico, my supervisor, and Jacob Biamonte. They had a paper. They introduced a density matrix for networks that was inspired by quantum mechanics, and its appearance is very similar to the thermal state that we have. As you see, I don't know if you see the cursor of my mouse, but at the top left, you see the row. This is the density matrix, and this is equal to exponential of minus some coefficient times a matrix. And,
we see the mouse. We see the mouse.
Okay, great.
You have just a window that probably you can hide on the bottom of the slide. This okay, that's perfect.
Thank you. Yeah, so this exponential matrix is very similar to what we have in thermal states in physics, exponential of minus beta Hamiltonian. And just to make it more interesting to you, that L matrix that you see, it's the Laplacian, but it is for the discrete space that describes networks. And you probably see the connection here, right? In quantum physics, we have the kinetic term of the Hamiltonian, Schrödinger's Hamiltonian, that is the Laplacian times a coefficient. So it is very similar to what we have in quantum physics, and they show that it has applications. They use it to infer some properties of real-world networks, and based on that, you can have the von Neumann entropy, the Kullback-Leibler entropy divergence, etc. When I joined Manlio in 2020, I had the pleasure to work with him on the same problem. We discovered that this density matrix is actually describing the information dynamics in complex systems. And how it works is like we perturb one of the nodes, there is a perturbation on top of that node, then there is a propagation that we consider it to be linear. So we are approximating the propagation of information in complex systems. And then when you stochastically perturb different nodes in your network, you get different patterns as responses of the network to your perturbations. And then when you superpose all of them together, you get this density matrix. And we also show that canonically it corresponds to an ensemble of information streams that guide the flow of information in the system, and they are weighted by Boltzmann-like distribution probabilities. One important thing is that this approach is also multi-scale. So as you can see in the top picture, in the first one, when time is equal to 0, the perturbation remains on top of the node, while when you increase time, the perturbation propagates to neighboring nodes, then it receives to all the nodes inside the community. So you see different levels of unfolding the dynamics and different propagation scales. You can tune this time here, that is a temporal scale, or we call it propagation scale of the dynamics. And then you can get short to long range interactions between the nodes, short to long range flow of information in the system. I'm going to give you some examples of applications. Some of them we are going to use directly in the recent paper. So one of them is very important. This is response diversity. We show that in two papers, we have shown that entropy, von Neumann entropy, measures the diversity of response to perturbations. Assume that you are perturbing one node, and then there is a pattern of propagation emerging in the system, and you perturb another node, and there is another pattern of propagation. If these two patterns are very similar, they have a lot of overlap, then the system is not really diverse in the way it responds to perturbations. Whereas if the patterns are very dissimilar, then your system is responding diversely to perturbations. And we show that topological complexity in the structure helps the functional diversity, helps the response diversity, or corresponds to higher von Neumann entropy. And we use that in case of brain studies to distinguish healthy and Alzheimer brains. We have recently generalized the framework to nonlinear dynamics as well. You can see it in this PRE that was published a couple of months ago. And another important property that I'm going to use in the following slides is the partition function. We have shown that the partition function encodes the dynamical trapping. Dynamical trapping is the tendency of the structure to block the flow of information. Assume that there is a network in which the flow of information from one part to another happens very quickly and efficiently. This network has low dynamical trapping and low partition function. Whereas in a network where the flow of field would be trapped in the neighborhood of the initiator node, then in that network you expect a high partition function and a high dynamical trapping. I'm not going into details for these papers, but if you had any questions, I would be happy at the end of the talk to go through it. But anyway, we use that to show, for example, that the transport properties of the multi-layer systems is always better than the average geometrical average of its layers. What is a multi-layer? What is the transport property? The transport property is related to the dynamical trapping, but I can explain to you what is a multi-layer if there was questions. We have used it to encode robustness, to measure the robustness of networks. We show that if you attack a network by removing the nodes that are very important for the diversity of response to perturbation, for the von Neumann entropy of the network dismantles quickly. And also the flow of information in the network would be dismantled quickly. So it is very important. The nodes that keep the response diversity high, they are very important for the robustness of system. Also, we used it for system comparison. I'm not going into detail on that, but we can use entropy and free energy, for example, as two coordinates to distinguish different networks and cluster them. There is also other very cool applications of our framework. There is this Laplacian renormalization group for heterogeneous networks recently published in Nature Physics that goes from a network of large size to a network of a smaller size. I think this is very much in line with the previous talk that we all enjoyed. So now that you have an idea of what is a density matrix in network science, network density matrix, I'm going into the new and recent work that we did. And firstly, I'm going to talk about response diversity versus coordination. So real-world networks receive external and internal perturbations. Either the perturbation comes from the environment, for example, your brain receives signals indicating that the sun is in the sky, it is morning. And then the brain should respond to this perturbation, this outside perturbation. And this response should be diverse. For instance, assume that there is one signal that tells you that the sun is in the sky, so you should wake up, and another signal that tells you that the sky is dark, so it may be time for sleeping. And these two require two different responses. If the system is not very diverse in the way it responds, then it's not a good news. And also there is a requirement for fast coordination. If I see a fire somewhere, my brain should coordinate all my body. So there should be a flow of information from my brain to my body, and it should be fast and it should be harmonic so that I can escape from that. And this is very interesting because what you see is these two factors, the diversity of response and the coordination, the flow of information that is necessary for the fast coordination of individuals in the network, are in conflict. They don't go hand in hand. So network backbones fundamentally limit the node's independence. If the nodes are disconnected totally, they can provide the most diverse response to external perturbations. Whereas network backbones help the flow of information and help the coordination. So there is a conflict between these two factors. And we started to guess that maybe this conflict explains why we see complex topological features in real-world networks. Let's do it more mathematically and more rigorously. So assume that there is a bunch of nodes that are totally disconnected, and then they decide at some point that we want to shape a network, we want to connect, we want to wire up. This is the thing you see at the top left. When we do that, there is a change in response diversity and there is a change in information flow in these systems that can be captured using von Neumann entropy and free energy, as we discussed in the previous slides. You see on the right side that I considered 4 very simple cases, the networks of 3 nodes that have either no connection, or they are fully connected, or they have 2 connections or 1 connection. As you can see, for instance, let's focus on the network number 4, that is the fully connected triplet. The perturbation happens on top of the top node, the right node, the bottom node, but the response to perturbation is the same. In all cases, all the nodes become red, all the nodes become perturbed because the network is fully connected. It doesn't have a wide dynamical range, a wide range of responses to these perturbations. So it has a lower entropy, von Neumann entropy, but it has a very high information transport. As you can see, delta F for it is quite high. The information propagates very fast through this. And the opposite case would be network number 1, that is a triplet that is not connected. You see the maximum response diversity you can expect from a network of 3 nodes, 3 different responses to the perturbations, but there is no flow of information in this system. And the complexity probably happens somewhere in between, and we are going to do that. So the important thing is that when you go from a network of isolated nodes to a network of connected nodes, there is a change in the von Neumann entropy. There is a change in the free energy of the system. And these two can quantify the change in response diversity and the change in how quick the signals can transport in the system. Let's do it more mathematically. I quantify a loss function Q that encodes the change in response diversity. Why do I call it loss? Because as I showed you before, the maximum response diversity corresponds to the isolated nodes. So when you wire up, you are reducing the functional diversity. You are reducing the response diversity. And we define a gain function W that encodes the change in perturbation transport. When W is higher, then the network is probably more connected. It allows for faster transport of nodes. And yeah, you can define it based on the entropies and free energies. And if you look at it, it sort of reminds us of the work and heat in thermodynamics that we know it. So it is mathematically similar to that. It is quite similar also metaphorically. It is not the same, but this was a part that was interesting to me personally, so I just wanted to share it. And there is a trade-off between this Q, the loss, and this gain, the gain that this W, the gain that you have during the network formation, that we define as eta. So eta is just the Q plus W over W, and Q is always negative. So eta would be between 0 and 1 here. We show that mathematically. And how it relates to the sparsity, the scaling laws, I'm going to go through that. I'm not going to spend a lot on the mathematics, but if you had any questions, I will be happy to try to address. So we start from eta, we tailor expand around small values of tau, meaning that we are looking at propagation scales that are small, but not very small, because we go up to the second order approximation. And then we make a number of assumptions, like the number of links in the network scales with the number of nodes, n to the power of delta plus 1 is proportional to the number of links in the network. And then from that, we obtain a simple expression for eta, for the trade-off between loss and gain during network formation process. And by maximizing it, we predict that the number of links in real-world networks should scale like n to the power of gamma, where gamma is just 1. So this is the prediction of the theory, of the theoretical framework. And here you see a bunch of simulations. I'm talking about the first column here, that is the difference between disconnected and connected. What you see on the left-hand side of the heat map is a logarithm of tau, the propagation scale. And what you see at the bottom, the x-axis is the logarithm of p, the probability of connectivity. On the left-hand side, we have a fully disconnected network. On the right-hand side, we have a fully connected network. And there is random networks in between. And what you see is that at a very specific value of p, we have a peak of efficiency. You can see it in the bottom figure here at different values of tau. And this value is close to 1 over n, or n to the power of -1. That is exactly what we expected it to be. There are other cases that we have explored, right, like segregation versus integration, order versus disorder, and we see that complex topological features favor this trade-off in some way in both of them. I'm not going into details in that as well, but I will be happy to discuss it afterwards. And at the end, we have the empirical allometric scaling. So we considered 543 empirical networks. They are taken from ICON, Colorado repository. They are from different disciplines: informational, social, biological, technological, economic, transportation. And they cover 6 orders of magnitude. The number of nodes go from 100 to 10 to the power of 8. This is the same for the number of edges, more or less. And what we observe is that the empirical exponent for this scaling is quite similar to what we obtained theoretically from the optimization of eta. So we go to the conclusion. Networks must balance between response diversity and their transport properties. This is the first point that I want to emphasize. To optimize the trade-off, complex topological properties are needed. The topological properties that we started this talk with are needed to optimize eta, in fact. And the allometric scaling that we observe in empirical networks can be explained using a framework that optimizes the trade-off between response diversity loss and the information transport gain. So whatever I said today is now on archive. You can check it out if you want, and you can write to me if you had any questions. Thank you for following this talk. I would like to send a special thanks to Manlio De Domenico, my supervisor, that is probably here still. He was here when I started. And also I would like to thank my collaborators through the years that made it possible for me to do all the research that I did during my PhD. And thank you for attending to this talk. I hope that it was good. I will be happy to receive questions if there is any.
Thank you. Thank you, Arsham. Is there any comment or question?
Yes. In the last slide, you used many network to study you. Are there all binary network in the sense? Did you do any studies on weighted networks or directed graphs?
Thank you very much. Yes, they are binary networks because otherwise we don't have a way to scale for instance, if I have a weight of 11 in my brain, and then I have a weight of 3 in the London subway, I don't know how to compare these two weights together. So yes, we are sticking with the binary networks to do that. And also the derivations, most of them are on binary networks.
Okay, and do you know if the Laplacian approach could be generalized to weighted network?
Yes, that's a brilliant question. In conclusion, we are exactly mentioning that. So this is only the first step, because most transport phenomena that happen linearly can be approximated in terms of diffusion, something like that, but they are not exactly that. So we have the framework to generalize that. We know how to make density matrices based on nonlinear dynamics. Then there is a need for other people to generalize our approach, and also there is a need for domain experts to choose the best equations that describe their domain of expertise, like the brain. What brain dynamics equations should I use? So there's a lot of place to for further works, I think.
Okay, thank you.
You're welcome.
Any other comment or question? I have just a brief question concerning, can you provide, I mean, you were showing the scaling argument. Can you just illustrate the scaling argument with a specific example concerning the balance of the trade-off?
Okay, so how about that simple triplet example? Let me share again, and I go there, and we can discuss that.
In the case of the triplet, it's a very small example, yeah, you know.
Yeah. So in larger systems, when you have isolated nodes, assume that all nodes are totally independent, so the dynamics of one doesn't affect the other one. And if I want, I can maximize the response diversity in this system. Each of the nodes is an independent agent that that's responding to the environment. But then there is no flow of information between them. So if there is a danger, a threat somewhere, they cannot inform the rest, they cannot coordinate. And this is how we can distinguish the extreme cases, like the fully connected network from the isolated network. And the complexity happens somewhere in between.
Okay. Any other question or comment? So if not, I think we can close the session of today. Let's thank again Marco Giulini and Arsham Ghavasieh for their talk, and see you next month for the next pair of young seminar. Thank you very much to all of you that have attended, and thank you again to the speakers. Ciao.
Ciao Rosario.
Ciao, Mario.
Thank you.